Good afternoon. I'm Carlos Cabo from Spain. So we are going to start the third session presentation. So we will have 6 presentations of 12 minutes. To the presenters, I'm going to show this sign after 9 minutes. And then we are going to have 5 very short 2-minute presentations for 5 posters. Only 2 minutes, please. And then after that, we will have coffee and poster sessions for 1 hour. Okay. So our first presenter is Markus Eichhorn from Ireland, who's going to talk about what it is, the leaf area of a tree. Please.
Sure. Take this. Good afternoon, everyone. I'm aware that I'm the first speaker after lunch, and so you're probably all slightly dozing off now, and therefore it's my job to wake you all up again by talking about leaves. And this is, for some of you, a slightly hard sell, because often when point clouds get processed from forests, the first step is that you filter between the wood points and the leaf points, and the next step is you throw away all the leaves. You know who you are. Actually, I'm going to try and convince you that the leaves are the interesting parts and that we should be trying to learn as much as we can from them. And that's because if we want to understand forests as systems, really it's the leaves that are doing all the work. They are the exchange surfaces of your forest. They are the surface that determines rates of photosynthesis, of respiration, of transpiration. They're the surface that determines the environment within the forest, because they determine the way that light moves through the canopy, the way that water and air move through the canopy as well, so they shape everything that goes on beneath the canopy. For many organisms, they are their living surface. There's a very old ecological hypothesis called the ecospace hypothesis, which says that you can apply the surface area, the species area relationship to habitats, and habitats with larger surface areas have more species in them. We've never been able to test that hypothesis. But if we know the surface area of leaves, we know the habitat area that's available for things that live on leaves. And for many of those species, in fact, most organisms in forests, they are also eating those leaves. Most organisms in forests are herbivores. And so this is literally the basal resource for the whole ecosystem. So we need to know how much leaf there is in the forest. The trouble is, it's not that easy. There's a few problems with leaves, the first of which is that although we've got very good at definitively identifying wood, we're very good at saying which points are wood, a definitive definition of leaves is a little bit trickier. Not everything that isn't a wood surface is automatically a leaf surface. They're also very heterogeneously distributed within your 3-dimensional space with varying density. You have large gaps, and then you've got clusters of leaves. They're a highly fragmented surface. You've got lots of edges, lots of blockages of leaf layers, which means you can't see them all from the ground. And the real challenge is that we're collecting point clouds, and leaves are planar surfaces. So at some stage, you've got to find a way to turn this large web of points you've created into planes. And the reason I want to do this is I want to try and move beyond leaf area index. Leaf area index is great if you want to look at the ecosystem level approach, if you have a large block of habitat and you want to work out how much leaf there is per area of land, that's probably okay. But if you want to really understand the 3-dimensional structure of your forest, you've got to work out where the leaves are. So the first thing we tried in this was a voxel-based approach. This paper here was published a few years ago, and I'm actually taking out a detail that wasn't part of the paper itself, but just to give you an indication. We scanned 40 woodlands across the UK, mostly oak, ash-dominated woodlands, and this was using a farrow. You can see there, that's our old PhD student Joe Riding doing the work, and we broke the point clouds down into 1 centimetre cubes, so voxel size was 1 centimetre. If you're not familiar with this type of processing, then really what we're doing is turning our point cloud into something that looks like Minecraft. Within each of those 1 centimetre blocks, we said, did it contain leaf or not? And we found that of all of the potential voxels within the forest, only about 0.05% of them contained leaf. So the first thing I'd like you to bear in mind is that not much of the forest is leaf. Although the forest looks green, the actual volume it occupies is tiny. I don't want you to put too much store in that specific number for two reasons. It's wrong in both directions, up and down. So it's a massive overestimate in the sense that even if a leaf goes straight through a 1 centimetre cube, only at most 10% of that is leaf. So that estimate is probably 10 times too high. But it's also biased in the other direction because we're not seeing all of the leaves. And the higher you go in the canopy, the fewer you're seeing. So it's biased in the other direction too. So I don't want you to pretend that's a real estimate. It's just an indication. What we can do, though, is get some fine-grained information about the distribution of leaves. This is what all of the individual surveys look like. And here I'm just showing you volume of data rather than trying to draw any general points. Each of these is a woodland in the UK. And as you go from the bottom of the plot to the top, you're seeing the number of voxels that contain leaves from the ground right the way up to the top of the canopy. This is a replicable measure. You can do it in multiple forests. And what we did in this paper was using this as a sampling approach where you can compare the structure of forest depending on its management or the presence of deer and so forth. So it gives you foliage profiles that are comparable between forests, but they're not comparable within forests. What I mean by that is that when you're sampling using terrestrial laser scanning, the way you're sampling at the bottom is not the way you're sampling at the top, because the further you go up in the canopy, the less and less you're seeing. So as you go towards the top of these plots, they become less and less reliable in terms of the foliage that's present. How much are we missing is the question then. And I got quite bothered about this a few years ago. We often refer to it as the occlusion effect. And I try to explain it in the famous terms that Donald Rumsfeld used when he was talking about intelligence in the Iraq War. We have known knowns, known unknowns, and unknown unknowns. So when you're scanning with a laser scanner, the first point is a laser scanner doesn't measure stuff. It measures distance to stuff. So you start from your laser scanner and a beam goes out, and that beam is a vector. And as it moves through space, there is nothing. And you know that there's nothing until it hits something. That something is a known known. You have a point. You can imagine that vector continuing in space. And you don't know what that vector would have hit next. If anyone wants to talk about multiple return LiDARs and split beams and so on, please don't. I've lost a lot of sleep over those. But generally, the beam, as it goes on, you don't know what's happening. So you have known unknowns. There is space that you are aware that you have not sampled. And the other thing that happens is the further away you go from your scanner, the more the beams diverge in space. However high resolution your scanner is, once you get 10 meters, 20 meters, 30 meters away from it, the gap between your beams increases, and so you have unknown unknowns. There are parts of the canopy that you just cannot see. How big are those? And how much are we missing? Well, this is where I brought in a computer software specialist, Dr. Ting Yun, who is now based at Nanjing Technological University, but did a placement with me for a postdoc in Nottingham a few years ago. And we explored this by creating very high-resolution virtual canopies. These are complete simulated canopies of genuine trees. And they were collected by Sylvain Pansbourg, who is a wonderful collaborator. And I don't suggest anyone ever repeats this work. What he and his group did, they took a very high-resolution single-beam laser and they mapped the individual positions of single leaves on a set of orchard trees. So for every individual leaf on those trees, they know its exact spatial position, its size, its angle. They even measured the roll of its lamina. So with this data, we can reconstruct the true leaf area virtually of full canopies. So we've got the ones we chose as 40-odd thousand individual leaves in space. If anyone wants this data, I'm very happy to share it with you. So is Sylvain. Just come and talk to me afterwards. It's freely available. Just please, if you do use it, credit Sylvain and buy him a drink because he deserves it. What was missing from this data set was branches, and we went to great lengths to stitch together a branch network for these leaves, and for reasons I'll come to, it turned out not to matter at all. But for the purposes of this study, we put together this virtual laser scanning environment and then worked out what we could see. And we did it with one virtual terrestrial laser scan from one side, 3 terrestrial scans, which is the standard, simulated an airborne laser scan, and then just as a kind of fantasy experiment, what would happen if you put them all together. And because we knew the true leaf area, we knew what we were hitting with virtual scans, we knew what we were missing, and we could work out how accurate our representation was. In order to get the leaf area together, we stitched the points into surfaces using a triangulation algorithm. This basically takes sets of 3 points that are close together and treats them as a surface, and then for contiguous ones, puts them together to reconstruct a leaf area. This has a threshold parameter so that the triangles don't get too big. If the triangles get too large, then you start linking between leaves and it goes all wrong. So you have to calibrate this with a data set to work out what the right threshold is, but then you can use these triangles to work out what the leaf area is from your point cloud and compare it either to what we know the true area should be or what a perfect scan would have come up with as a control. What we find is that adding branches doesn't really make any difference. This shouldn't surprise us. Leaves block our view of branches. Branches don't really block our view of leaves. So the branches turn out to not be important. With a single scan, we get about 1/3 of the leaf area. With 3 terrestrial laser scans, which is the default, you can make up about 67%, so about 2/3 of the tree leaf area doing this. If you just have airborne, you only get about 1/3 of the leaves, but you get different leaves. The reason being that most of the leaves over the top of the canopy are held flat, and so looking straight down, you see this flat surface of leaves that hide everything underneath them, but you also don't tend to see them so well from below either. So in a perfect world where you could combine these approaches, you can get over 80%, up to 90% of the true leaf area of the tree by stitching these together. Sounds impressive? Yes. It's also, let's be honest, not fully achievable in the real world, at least not with the technology we have at the moment or the processing. The things we've got to compensate for, and several of you who talked this morning will I want to talk to you about this, is what we do about leaves in motion. We have some ways of solving this. Closed canopies are a challenge because you've got overlap between trees, of course, and we were only dealing with trees up to 10 meters high. What happens when you get into the trees that are 30, 40 meters high? Honestly, we don't know. And then finally, I said that if you could integrate TLS with ALS, that would be brilliant. We can't do it at the required resolution yet to make that achievable. So I say it's a fantasy, but you know, this is the tantalizing goal that's out there if we ever manage to do it. What are we using these for? Well, a couple of applications. We're working on segmentation to identify individual trees and canopies. We're getting better at doing that from above. Airborne laser scanning, we're actually getting quite reliable at that, but from terrestrial laser scanning, we're not. But that's where having these branching network models comes into play, and we're finding those are working a bit better, but we're still going on that. And then someone's bound to ask, what about trees with needles or thin leaves? Well, you can't treat them as surfaces anymore. So the idea that we're playing with at the moment is treating them effectively as Gibbs functions, to have a 3-dimensional probability space of something moving through it. I say that it sounds very simple. It really, really isn't, and there's some physicists being very busy and getting frustrated right now. So we're trying to use these canopies for a range of applications that I'm happy to talk about, and I'd love to find ways to integrate them with the other modeling frameworks that people are using here. But I'll leave it there and give you the suggestion that I think it is possible to get a direct measurement of leaf area without even touching a tree, potentially seeing something like around 2/3 of the leaves. Whether we reconstruct that accurately, we'll find out, but we can do it. The big skill gap that I'm finding personally is in computer graphics and computer vision. That's not because the techniques aren't well developed, it's because the people with those skills go into other industries where they get paid a lot more than I can. So getting the insights from computing, particularly software developments and gamers, is going to really transform our ability to turn these point clouds into something that looks more like the real world. So thank you very much, everyone.